All right. This is a lecture for Thursday, 11:15. We are going to cover the rest of Chapter 5 here after we do the bell ringer. So you should have your lab reports back. I will get your quiz grades posted just as soon as I get those graded. I have no idea when that'll be. But y'all probably don't care because it's about to be Thanksgiving break. So let's dive right in. We got a good bit of stuff to cover, as you can see over here, guys. We're going to work this bell ringer really quickly to refresh you on some of this stuff, and then we'll check back in after Thanksgiving. All right, so our problem was 12.84% sulfur, and then it was 25.45% copper, 25.63% oxygen, 36.07% H2O. It's not normally how we'd write that, but they're clearly trying to help us out, keeping those separate with the oxygens there. Okay, and then once we know that, we're going to name it. Okay. All right, so how do we do this? All right, so the first thing we got to do is we got to convert them all to moles. Okay, and that's easy enough to do. If you guys remember, 12.84 grams. Remember, we pretend like we've got 100 grams of the compound. 12.84% of that's 12.84 grams sulfur, and sulfur is 32.1 grams per 1 mole of sulfur. Okay, and that comes out to 0.4 moles of sulfur. Okay, you do the same thing for each of the other ones. All right, and we get 0.4 moles of copper, 1.6 moles oxygen, and 2 moles of water. What do we do? All right, so this is clearly supposed to tell us that it's a hydrate because it's an H2O. So let's write it that way. We'll write it as sulfur. We write them as a subscript. Even though that's not proper right now, we're going to use that as a shorthand to keep up with what we're doing. And then remember, hydrates have that dot right there. And then we're going to do H2O, and we're going to do like this, and we're going to do 2. So we can keep track of that and not lose our way there. All right, then we find the smallest one, and we divide by it, which is 0.4 here. So then we divide by 0.4 all of them, and we get S1, it's copper 1, oxygen, 1.6 divided by 0.4 is 4. 2 divided by 0.4 is 5. So we do 5 like that. Okay, so then we rewrite this SCuO4 H2O 5. Okay, so this is not quite right here. Okay, because there's no way we have to name something that's kind of weird like that. But if you'll flip back to your polyatomic ions, our new best friends, okay, on page 133, what do you see there that could be rearranged to make up? There is no copper anything on that list, but there is an SO4. Okay, so this is a copper SO4 H2O 5. So this is a copper sulfate. Okay, but we're not quite done because that copper takes multiple valences. Well, no, we are done because sulfate only takes a 2- valence. Okay, so it's done. We don't have to identify the oxidation state here because it has to match that one because we already know. Okay, so I think we would say copper sulfate hydrate because of the water in it. Okay, now offhand, I'm actually not quite sure whether we have to specify how many waters are hanging out in there or not. Okay, let me actually look this up really fast. I should have looked this up before. Not prepared. Terrible. Okay, he does. He says copper sulfate pentahydrate. So we need to indicate that 5 with a penta. Okay? All right, that's our bell ringer. Y'all pause and talk about it if you need to. I'm going to move on because I've got a bunch of stuff to cover here. All right? So, where did we say? 5.3.9. You'll flip over there. Okay, we did resonance structures, exceptions to the octet rule. We're going to spend a little bit more time on that and practice on that if we have time today. All right. Naming binary covalent compounds. Okay, remember we had a PCl3. We just write the first one, and then it's 3 of these, so it's trichloride. Okay. N2O4, 2 of those, so dinitrogen. 4 of these, tetroxide. Okay, which is a slight shortening of tetraoxide. Okay, all right. Energy in covalent bonds. All right, so we're kind of back to talking about some of this, one of these primary concepts in the chemistry deal here. Got a little bit of a glare there, sorry. So the covalent bond and ionic bond are quite different from the perspective of quantum mechanics. Ionic bond held together by electrostatic attraction between ions. Okay, so remember we're transferring that electron from one to the other. One gets a positive charge, net, and then one gets a negative charge, net, and then they attract like magnets. Okay. But the covalent bond is held together because of the energy minimization that occurs within the atomic orbitals when they share, basically. Okay, so basically what he's saying is, it minimizes the energy when they are covalently bonded. Okay, so there was let's say a sulfur and 2 oxygens hanging out there. And when they got near each other with a certain catalyst or in a certain temperature, whatever, they actually come and they're coming down the energy hill right here. Okay, so they're minimizing their energy. Anywhere they go is a higher energy state, so they don't unbond unless you give them that energy to push them up that hill. Okay? All right, and so he just kind of gives you for instance, with 2 hydrogens. Okay, and then basically they come together to a certain distance that minimizes their energy. Okay, now that's different for each one, and they experimentally find this stuff, but he wants you to notice that you're minimizing energy like he's always talking about. Okay? All right, and so we just want to very quickly note a couple of things here. Distance between the atomic centers in the molecule. No, between the atomic centers, okay? Not this distance right here between the outside of the electron clouds, but between the atomic centers right here, okay? That's our bond length. Distance between the atomic centers in the molecule is called bond length, okay? They show bond energy here, which is the energy required to separate or break this bond. Okay, and that's kilojoules per mole. So you got a whole mole of H2. You got to put that much energy into it to break all those bonds. Okay, bond length P. What do we know? Picometers. Okay, 1 times 10 to the -12th, I believe. Hold on, let me check on that. I think they're a tenth of a nanometer. Once again, not prepared. You know, you get old, and you think all this stuff just sticks in your head, and it just doesn't anymore. There it is. So, B and then A. Here we go. It doesn't even have it there. Anyway, y'all look it up. Somebody Google it. What a picometer is. Anyway, that's what that PM is for. I'll look that up and I'll know that next time we talk. Right, so 2 key points. Generally speaking, double bonds are stronger, which means a higher bond energy to break them. Okay, the stronger a material is, the harder you got to pull on it to rip it. Okay, same with bonds. And triple bonds are stronger than double bonds. Makes sense. 3 strings are stronger than 2, which are stronger than 1. Okay. All right. So this explains why nitrogen gas is so unreactive. Hard to break those bonds to get it to do anything as a reaction. Okay. 79% of our atmosphere, which is good. Things aren't exploding all the time. All right. And it makes but oxygen molecules react all the time. Okay. 498 kilojoules per mole to break that, while it's almost double that to break the nitrogen triple bond. Okay. And second, as the strength of the bond goes up, the length of the bond shortens. Okay, so basically the stronger the material, the tighter it's pulling those together. Okay, and that's all we're going to really need from there. Physical properties of covalently bonded substances. One of the results of the weak forces, so they're not nearly as strong as the ionic bonds. The forces holding one molecule to another. Sorry, I moved my page before I was ready to. Forces holding one molecule to another, which we study in the next chapter, are much weaker. Okay, so weaker bonds than ionic bonds, which is why many of the common covalent compounds are gases or liquids at room temperature. Okay, they have much lower melting and boiling points. Okay. Okay, compounds that are liquids at room temperature, water, bromine, one of only 2 elements that are liquids at room temperature. What's the other one, guys? Y'all know? Mercury. Okay, it's kind of interesting to think about that of all the elements, only 2 are liquids. Most are solids, and a lot are gases. So just kind of weird that that's like a small window for that. Okay, and just, kind of note this: less soluble in water, less electrically conductive, and less thermally conductive. That means heat does not move as easily through them, and electricity does not move easily. All right, so moving on to electronegativity, polarity, and bond character. Okay, remember we talked about electronegativity? Okay, so we had this chart right here. Remember we had the Pauling scale, and we had this number here. The higher the number, the more electronegative, with fluorine being the most. Okay, and remember that's not just attraction to random electrons, that's attraction to the electrons that are in that bond. Okay, and so looking at this right here, if a molecule is composed of two identical atoms, such as H2, they're exactly the same, the electronegativities. They're both 2.2 for hydrogen, obviously, right? It's a hydrogen and a hydrogen. All right, so it's a non-polar covalent bond. Okay. And he said he has an image here. So what do we have right here? Okay, so that's nice and symmetrical. Okay, nice symmetrical molecule there. Okay, that's non-polar covalent. So we're talking about covalent bonds, and that's the non-polar version. Okay. All right, and then we move to something like HCl. If you look at those electronegativities at the back of the book, H is 2.2, and chlorine's like 3. What does he tell us right here? Yeah, 3.16 for chlorine. Okay, so the higher electronegativity of chlorine results in the shared electrons being pulled over to the Cl, to the chlorine atom. Okay, they're squished this way. Okay, they're pulled that way, and what that does is results in a partial positive charge here and a partial negative charge there. Okay, all right, and that is called a dipole. Di, two poles, pole, right? So we got a dipole there, and just the positive and negative ends with the delta plus. That's a lowercase delta. Okay, whereas a capital delta is the triangle. It's a lowercase delta. Delta plus and minus. All right, and then he shows us that in print we would show it like that. Okay, with the arrow pointing towards the more electronegative to indicate which way the electrons go. Okay. All right. The polarity of the water molecule that we discussed previously is so important that we consider it again here for just a minute. The shading of the region around the water molecule illustrates how the electrical potential changes from positive to negative. And so he's kind of shading it to show us what's going on. And remember we talked about how these positives like to line up with the negatives, and that creates a secondary hydrogen bond. So there's your covalent bonds right here, and then between this water molecule and the next, there's a hydrogen bond, which makes it really hard to boil, which makes it liquid at room temperature and not so easy to evaporate. If you ever put like rubbing alcohol on your hand, it feels very cool. It's because that alcohol is evaporating very quickly. You pour out a puddle of alcohol and you blow on it, you can watch it evaporate. Okay, so it's much easier to evaporate because it's non-polar and doesn't form those. Well, it is polar, but it doesn't have those hydrogen bonds, and so it's not as linked one molecule to the next, and so it's easier to break those and have them turn into a gas. Okay. All right. So here is a sort of topic that's going to show up on a test right here. I even wrote very important when I was reading through this earlier. Okay. So we want to note something here that our descriptions of the electrostatic forces in ionic bonds and the electron sharing and covalent bonds are simplistic and fall short of being complete descriptions. So what does that mean? It means there's more complexity to it than we're really going to cover, okay? And thank God for that, right? Because that's much more complexity, and if you guys ever take like a serious chemistry class, it'll be really cool to learn all that, but it'll be a lot of work, and it's beyond the scope of what we can learn here. Okay, but what's important here? Okay, the scale in figure 5.24 is used to characterize atomic bonds as non-polar covalent, polar covalent, or ionic. Okay, so we talked about them being non-polar when they're 0. Okay, so 0 up to I don't know that we have a lower bond that's between here. Okay, it looks like 0.9, something like that. Okay, we would say that that's where it transitions from nonpolar to polar, maybe a little bit less than that, 0.8, 0.7, something like that. Okay, but once we get about, we see right here this HCl, that's definitely polar, and it's only 0.96. Okay, all right. So as we move up, the more distance between the two atoms involved, the more they start to act like an ionic bond, okay? So it's not a clean break, right? Like these atoms bond covalently, period. And then these over here bond by a completely different mechanism, and it's ionic. It's more like they share the atoms, and then if they're electronegative enough, we get enough of this action going on that it's really more like that electron actually gets transferred. Okay, so do you see how like maybe somebody has borrowed your hairdryer so many times that they've basically just taken your hairdryer, right? Or they've borrowed your books so many times and have kept them for so long that they really just have stolen your books. Okay, that's kind of the deal. So that, you know, how many times you have to borrow somebody's hairdryer before you really have borrowed it too much? Well, it's kind of hard to tell. Okay, that's kind of that gray area right here. Okay, and so they're saying when here's the key, 1.7, the bond is considered to be 50% ionic, and for anything greater than that, the bond is considered to be essentially ionic. So if I ask you on a test, on a quiz, you know, let's look at hydrofluoric acid. Okay, we would come over here and I'd say, what is the general bond nature? Polar covalent, non-polar covalent, or ionic. You'd say, all right, well, this is 3.98. That's 2.2. The difference in those is 1.78. So we would say that that is essentially ionic in character, right? Because it's above that 1.7. Okay, and it's pretty, you know, like I said, it's it's a sliding scale there, but for our purposes, we're just going to pull the trigger at 1.7. Okay, so if I'm going to ask you about nitrogen, N2, I'm going to say that it's bonded to itself, N2. That's always going to be non-polar covalent, okay, because it's the same element. So it's got to be non-polar. They have the same electronegativity, no matter what it is. Two fluorines bonded together is non-polar covalent, even though they're both very electronegative, very interested in pulling electrons away from the partner that they're bonded with. They do it in equal amounts, and so they're not polar. Okay, and we will see how this affects solubility later on. Like dissolves like, polar things like to dissolve in polar things, but we don't have to cover that now. It's just we're giving you a vocabulary here about what polar actually means and how we break that down in terms of the electronegativity. All right, so that is everything I wanted to really cover from this chapter. Finally, we've made it through 5. After I look at your quizzes and how those went, I will start thinking about how to help us get ready for our test at the end of the semester. When we come back from Thanksgiving, I'm super glad you guys are going to have a break. You guys have done a lot of work, well, for me, and I know you have for others as well. So I'm glad you guys get a break. I'm glad I get a break. But when we come back, we will do another experiment, and then we will really just have the final exam left and another darn lab report. So I hope we have a really productive couple of weeks after Thanksgiving, and then we'll be on to Christmas, and you guys can start looking forward to that. All right, I'm about to be done here and let you guys do whatever I have left for the rest of your class. I'll talk to you guys after Thanksgiving break. Gobble, gobble.